Hi everyone, welcome to the Chemical Engineering Process Design Learning videos with Aspen Plus software. This is our second video lesson. This video lesson provides you knowledge and skills for using Aspen Plus software to analyze chemical component properties, using Aspen Plus software to generate vapor-liquid equilibrium curves for component mixtures. First, it's very important to understand why we should analyze component properties. We need them in design of every unit operation. This is only one example for your understanding. Extractive distillation is a technology that uses a third component or a solvent to separate two component mixture which are difficult to be separated by direct distillation. In selecting solvents, we look for components with normal boiling point temperatures which are little higher than the components to be separated. For such a case, we need to know the normal boiling point temperatures of candidate solvents. In addition, we should check the densities of them to ensure the two liquid phases formed during extraction have enough differences in density. We also need to check the selected solvent's density against the existing liquid phase so that we know which liquid phase is heavier. Methyl isobutyl ketone, otherwise MIBK, is a promising candidate solvent for separation of acetone and water mixture. Let's check whether the density of methyl isobutyl ketone is different enough from the density of water. We also need to determine the heavier liquid phase formed mainly by these two components. We shall use NIST component database available in Aspen Plus software for this purpose. NIST stands for the National Institute of Standards and Technology. It provides chemical and physical property data on over 40,000 compounds. You can use Aspen Plus software to obtain necessary chemical component data from this database. The advantage is they are most updated experimental data. So let's start Aspen Plus software. Create a new simulation in Aspen Plus using the blank simulation option. Specify methyl isobutyl ketone and water under the components. To retrieve NIST experimental data and perform property evaluation, click the Data Source NIST button in the Home ribbon. Select methyl isobutyl ketone under the components to be evaluated. Then click the Evaluate Now button and wait for the search engine to retrieve the data. Close the NIST Thermodata Engine window after the search is complete. Select the density of liquid versus gas option under Properties for methyl isobutyl ketone, and then click the Experimental Data sheet. Go to the list of experimental data from NIST, sorted by temperature, density, uncertainty, accept, reject, and citation. The accept reject column indicates whether the specific experimental data point serves an outlier or not. Note that the density for methyl isobutyl ketone is approximately 796 kilograms per cubic meter at room temperature. Click the Data Source NIST button in the Home ribbon again. Select Water as the component to evaluate. Click the Evaluate Now button to retrieve experimental data of water from NIST database. We can find the density of water is approximately 1000 kilograms per cubic meter at room temperature. The density of methyl isobutyl ketone is clearly less than the density of water at the same temperature. The liquid phase formed by methyl isobutyl ketone should be lighter than the liquid phase formed by water. Therefore, the aqueous phase formed by water should be at the bottom, and the other liquid phase should be at the top during the extraction process. You can also use Aspen Plus properties database to determine the component properties. Let's follow an example demonstration for that. Determine the vapor pressure of ethane at room temperature and its normal boiling point using Aspen Plus software. You all know that in chemical engineering, we refer room temperature as 25 degrees Celsius. Ethane is used in the production of ethylene for making plastics, antifreeze, and detergents. It's a substance in producing welding gas and a component in the natural gas too. Therefore, the vapor pressure of ethane is an important physical property for separation and its applications. Create a new simulation in Aspen Plus using the blank simulation option. We must first specify the component used in the simulation. Our problem has only ethane, so enter ethane into the first row under the component ID column and hit enter. The component ID is the user-defined parameter that Aspen Plus will use to report and identify components in a given simulation. Aspen Plus can also guess which species the user has entered based on the given component ID and retrieve physical properties from its databases. However, some chemical components with long names should be first searched from Aspen Plus databases. In this case, you can see that Aspen Plus has successfully retrieved accurate information for ethane from the entered component ID alone. Next, we should specify the property method that Aspen Plus will use to calculate physical properties of ethane. If you are unclear about property methods used in process simulations, please refer our first video lesson before continuing this video lesson. We can use the Methods Assistant as a help to select an appropriate property method. Go to the Methods Specifications and Global Sheet by pressing the F4 key or using the tree view in the navigation pane. Click the Methods Assistant button. Then Methods Assistant window will appear. Click the Specify Component Type link. Since we know ethane is a small hydrocarbon, we will select hydrocarbon system. In this simulation, we are not using pseudo components or petroleum acids, so select the corresponding option as no. The Methods Assistant is now displaying several property methods that are well suited to components like ethane. We will select the Penn-Robinson equation of state for this simulation. Close the Property Method Assistant window. Go to Methods, Specifications and Global Sheet. Set the base method field to Penn-Robinson, which is abbreviated as Penn-Rob. We are now ready to begin generating vapor curves for ethane using the Penn-Robinson equation of state. From the Home toolbar, click the PO button. The PO analysis sheet for PO component 1 is displayed. Note that the Run Analysis button at the bottom of this sheet is not enabled because the necessary inputs for the analysis have not been entered yet. You can see the selected property method has been already taken as Penn-Robinson in this sheet by default. Next, select the physical property you would like to analyze. In this example, we should select PL from the property drop-down list. Physical properties have been given unique identifiers in Aspen Plus. PL signifies vapor pressure of a liquid. Some commonly used ones are DHVL for enthalpy of vaporization and PHI for fugacity. Select the units for vapor pressure as bar. After selecting the required property, we have to tell Aspen Plus what to plot. In the temperature frame, set the start point to -100 and the end point to 25 degrees Celsius. In the components frame, select ethane from the list of available components and click the single right arrow. This will move only the selected items from the list on the left to the list on the right. Clicking the double arrow will move all of the items, which is useful for moving a large number of components. Note that the Run Analysis button is now enabled. Press the Run Analysis button. This will generate a plot of vapor pressure of ethane in a new tab. Note that at 25 degrees Celsius, ethane's vapor pressure is about 42 bar. Repeat the PO component analysis using the upper temperature as -80 degrees Celsius instead of 25 degrees Celsius. From the generated plot, the normal boiling point can be found at about -88 degrees Celsius. You all know that normal boiling point is referred to the boiling point at 1 atm pressure. Volatility differences which are indicated by the component's vapor pressure are very useful for separation processes involving vapor-liquid equilibrium. Higher vapor pressure means a component is more volatile. As we can see from the generated plots, ethane is a volatile component. At room temperature, its vapor pressure is about 42 bar. TXY diagram for a binary system can explain whether it is easy to separate the two components or not. If the X curve and Y curve are not close together, we can claim that there is no azeotrope. Then it's easy to separate the two components using simple distillation. If there is an azeotrope, we have to use advanced distillation technologies to separate them into pure components. Therefore, a TXY diagram is a very useful tool for process synthesis and search of extractive solvents. Let's generate TXY diagrams for ammonia and water binary system as well as benzene and ethanol binary system separately and determine their separation modes. Note that TXY diagram means the vapor-liquid equilibrium curve. Create a new simulation in Aspen Plus using the blank simulation option. Enter ammonia, water, benzene, and ethanol as components respectively. Click Next button in the Home ribbon. For methods, select Unique RK Property Method for base method. Click the Next button again so that binary interaction parameters are populated. To perform a binary analysis for the ammonia water system, click the Analysis Binary button on the Home ribbon. The binary analysis sheet is displayed. Select ammonia for component 1 and water for component 2. Select Unique RK method for property method. Select vapor liquid as the valid phases. After that, click the Run Analysis button. A TXY diagram for ammonia-water binary system is generated. We can observe that the Tx curve and the Ty curve are far away from each other. This means that separation of these two components using a distillation column is pretty easy. Repeat the same procedure for benzene-ethanol binary system too. We have generated the TXY diagram for benzene-ethanol mixture. We can see that benzene and ethanol form a minimum boiling azeotrope. Therefore, to separate these two components, a single distillation column is not sufficient. We have to go for a special method as described earlier. Let's discuss this further. Water and many organic components are immiscible or partially miscible. This can be observed in many separation processes. Sometimes a liquid-liquid extraction process could be more efficient than a distillation process because we don't need to vaporize much liquid in liquid-liquid extraction processes than distillation. To examine this, let's consider the binary system of water and cyclohexane. Go to the component sheet again and specify cyclohexane as a component. Select UniQuack for base method click the Analysis binary button on the Home ribbon. Select water as component 1 and cyclohexane as component 2. In the valid phases, select vapor, liquid, liquid. Generate the TXY diagram for the water and cyclohexane binary system. Note that there are 4 regions. In the region above the green line, only vapor phase exists. In the region within the left triangle, a vapor phase and a liquid phase that contains almost pure cyclohexane can exist. In the region within the right triangle, a vapor phase and a liquid phase that contains almost pure water can exist. Below the horizontal blue line is the 2 liquid phase region where a liquid phase contains almost pure cyclohexane and the other liquid phase contains almost pure water. Therefore, the diagram tells us that cyclohexane and water are almost completely immiscible. This immiscibility can be used to decide the separation process whether liquid-liquid extraction or special distillation technique is required. As well, this reveals that components like cyclohexane are very effective solvents for extraction and azeotropic distillation of binary liquid mixtures which contain water. A good example is water-ethanol mixture. Like this, you can use Aspen Plus software to generate vapor-liquid equilibrium curves and obtain information to determine their separation techniques. Since Aspen is equipped with latest updated chemical databases, especially students can use it as a library tool to retrieve more reliable chemical component property data for their manual calculation as well as simulations in various chemical and process engineering problems. I hope that you grabbed the knowledge and skills on some property analysis tools available in Aspen Plus software to study chemical component systems during the process design and simulation. Please watch our next video lesson about material and energy balance simulations in Aspen Plus software. Until we meet with our next lesson, Have a nice day and goodbye.